So question is saying a block of mass capital M is released from rest at point A. Height is 6r above the horizontal. So this is 6r.
Mm-hmm.
After being released, the block slides down as shown in this figure. When released from point A, the block does not lose control with the track at any point. So it does not lose control and it completes its loop, right? So at point B is this is what R and this is what R. So it is at 2r height, and at this point again this is 2r
Mm-hmm.
and this is 2r, right? So
Okay.
completely at 4. At point C, it is 4 are located at the highest point of their respective circular loop. Both radius are or frictions are negligible. Frictions are negligible. Okay. So in this question, first diagram A shows the energy bar chart that represent the gravitational potential energy UG of block or system, the kinetic energy K of the block at point A when the block is released from the rest at height 6r. Okay, so this is the graph for block earth system, and the energy is represented. So UG is what potential energy, and kinetic energy initially was 0, so that's why it was represented like this. So we have to draw a shaded region in diagram B that represent the gravitational potential energy UG and kinetic energy when the block is located at point B and at a height of 2r and above the horizontal. At point A, only the potential energy because the velocity is 0. So potential energy, so mg to sorry 6r it is. Okay, 6r it is. To mg 6r. And at this point, at point B, the what is the potential energy? Mg 2r, and rest of it means if you subtract the rest of this is the kinetic energy. Although I am writing in the form of potential energy only, but it is mg 6r minus mg 2r, right? I am not writing in the velocity, but for the comparison I am writing in this form. Okay, so it is basically the rest of it would be converted to kinetic energy. So the amount which would be converted to kinetic energy, that would be 4r. Okay, so it is 2 and it is 4 and this is 6. Okay, rest is same. So we have to like count the blocks 1, 2, 3, 4, 5 and 6. So this is 6. So to draw the MGH we have to draw till 2, and the kinetic energy is 4, right? So this
Mm-hmm.
is for kinetic energy.
Okay.
Next is the second part says starting with the conservation of energy, drive an expression for the speed of the block at point B. Express your answer in terms of R physical constant as appropriate. Begin your drive. Okay, so at point A it is just UG, and at point B it is potential energy plus kinetic energy, right? So at this point it
Mm-hmm.
is mg 6r, and at this point it would be mg 2r, and the kinetic energy half mv square. So we have to find the velocity, right? Velocity derivation we have, speed we have to find. So it would be m got just cancelled from all parts. So it would be 4r into g into 2, because of this denominator it would be 2 is equal to v square, or I can write v is equal to root of 8r. This is the velocity term in terms of r and constant. Okay, and then the next part, on the following dot represent the block, draw and label the forces, not components, that are exerted on the block at the instant block slides to point C. So at point C, how many forces are acting on this? Like we have to represent that.
Force of
mg
gravity. Yeah.
and
Force normal.
yes, normal is also acting in the direction because the velocity is greater than the minimum velocity. So that's why a normal force would also act on the in the downward direction. Okay, vertical circular motion. This is your object. Mg is at this point. Mg is acting this direction. Okay, and this is the center. So this is your normal force acting. If it is a track, okay, or a string, then it would be tension. But now, since it is a track, the normal would be acting towards the center. And when you reach at this point, mg is acting this way, and normal is acting like this direction. And when you reach at this top, mg is acting downwards, and normal is also acting downwards. This is the case where your velocity at this point, the velocity is greater than the v minimum velocity. Is a student claims that 4r is the minimum height of point A, such that the block can slide through the point C without losing contact with the track after the block is released from the rest. Explain why the claim is incorrect. A student said that this that minimum height required, like if it is 4r, then also this block would have completed the entire uh, path. So in this case, if this is at 4r height, okay, if let us say this is 4r height, what is the energy at this point? mg4r.
Yeah.
Okay, then what is the potential energy at point C? mg4r,
Yeah. So it's
right?
zero.
So
Yeah.
kinetic energy would be zero. So when it reaches point C, so mechanical energy at point A would be equal to the mechanical energy at point C, right? There is no friction, no loss. So this would be equal to this. So at this point, the kinetic energy would be zero. So the velocity would be zero. So it would fall. In a different experiment, so this is different setup. A student attached one end of the spring of the force sensor that is attached to the wall. The other end of the spring is attached to the cart of mass 0.25 kg. The student places the motion detector right to the right of the cart as shown in this figure. So this is motion detector. Whenever this cart moves, it would measure it. Okay, and the cart spring system oscillates. The following are the graphs. So velocity versus time graph and force versus time graph. These two we get. Okay. In part C, first part, the using the data of velocity time graph, calculate the change in the kinetic energy of the cart from time 0.25 second to 0.2 second. Let's see. 0.25 to 0 to 2 seconds till 2 seconds. So can you tell me the velocities at this point? We have to find the change in the kinetic energy. What is final kinetic energy? So
Square.
1/2 mass is same. So I can write Vf square minus Vi square. So what is the mass? 0.25. What is the final velocity?
At 2, it's 0.
Yes. And what is the initial velocity at 0.05 second?
Yeah, point 0.3.
zero point 0.3 square. Okay. So you just calculate this, how much you are getting, the change in kinetic energy.
0.01125 negative
0 point.
0.1125.
Now let's see the second part. Use the force time graph. Estimate the change in momentum of the card at 0.5 second to 2.5 second. Let's use this graph, and from this point to 2.5, this point, we have to find the change in momentum.
Force times the time.
Find this is time and this is force. So we have to find this area.
Yeah.
Okay. So area under graph. Okay. Between 0.5 to 0.25. time is equal to 2.5. If you see, this is negative area and this is positive area. So what is delta P change? Equal areas in opposite. This is positive, this is negative. So change in momentum is
0.
0. Okay. Data
Yeah.
from velocity. So now we have take help of the velocity time graph and confirm your estimation in this part. So delta P is 0 and this we have to confirm from velocity time graph as well. Let's see. So now between this and this point, delta.
Mm,
What is the velocity at this point? 0.5, 0.3. And at this point, what is the velocity?
0.3 also.
0.3, right? So 2.25 into 0.3 minus 0.3. So what I get? 0. So from the velocity time graph, it is also confirmed that the change in momentum is 0. Thanks for watching. If you like the video, then please like it and subscribe the channel. We will bring more problems along with the solution. So if you have any query, then you can WhatsApp me. If you want a private tuition from me, then you can scan this or send me an email on forcetra.physicss@gmail.com. See you in the next video.